Welcome to my classroom. In this video, I would like to talk about the four special lines in a triangle, namely the perpendicular bisectors, angle bisectors, orthocetres, and medians. They are concurrent, and the intersection points Circumcentre, Incentre, Orthocentre, and Centroid has some interesting properties. So this video is to enrich the topic learned in Form 3 and which are proved by some knowledge learned from junior forms to senior. Given 2 points, if they are not coincident, then there is a unique line joining them. But for 3 points, the points may not lie on the same line. More often, they form a triangle. When they are on the same line, we say that the points are collinear. There are many methods learned from junior forms to senior for checking whether 3 points are collinear or not. I'm not going to talk about the methods here. You may think about this. Extend these ideas to lines. If 2 lines are not parallel, the lines intersect at a point. If 3 non-parallel lines are given, usually they form a triangle. Yet, it can happen that they intersect at the same point and no triangle can be formed. In this case, we say that the lines are concurrent. If the equations of the line are given, we can find out the intersection points of 2 lines by substitution. See if the points satisfy the third line to draw the conclusion. In this video, we consider 4 special lines of a triangle and so that these lines are always concurrent. Also, the intersection points have some interesting properties. The first type of special lines we are going to discuss is the perpendicular bisector of a side. As there are 3 sides in a triangle, there are 3 perpendicular bisectors to consider. It is obvious that the 3 perpendicular bisectors are non-parallel. Interestingly, they are always concurrent. We learned in Form 3 that the intersection point is called the circumcentre of a triangle. That is, the center of the circle passing through the 3 vertices of the triangle. Have you thought of why the 3 perpendicular bisectors are concurrent? That is, how to prove the 3 lines always intersect at the same point. Also, why the intersection point is the center of the circumcircle of the triangle. You may pause and think about this on your own first. Here is the structure of the proof. We consider 2 perpendicular bisectors and the intersection point. Prove that this point also lies on the 3rd perpendicular bisector. Thus, the 3 perpendicular bisectors had a common point. That is, the 3 perpendicular bisectors are concurrent. Let M, N, L be the midpoints of AB, BC, and CA respectively. And the perpendicular bisectors of AB and BC intersect at O. Consider triangle OAM and triangle OBM. They are congruent by SAS. Thus, OA equals OB. Similarly, consider triangle OBN and triangle OCN. We have OB equals OC. Combine the results, we have OA equals OC. Now, consider triangle OAL and triangle OCL. They are congruent by SSS. Thus, angle OLA equals angle OLC and equal 90 degrees. That is, OL is perpendicular to AC. In other words, OL is the perpendicular bisector of AC. So, O is the point lying on the three perpendicular bisectors. The proof of concurrency is done. It is easy to answer the second question, why the point of intersection gives the center of the circle passing through the three vertices. Due to the congruent triangles, we see that OA equals OB and OB equals to OC. So take O as the center and OA as the radius. The circle passes through B and C as well. Therefore, the circle drawn is the circumcircle of triangle ABC and O is the circumcentre. We can make use of the similar structure of arguments to prove why three-angle bisectors are concurrent, and the intersection is the center of circle inscribed inside the triangle. Pause and try. Let the angle bisectors of angle A and angle B intersect at O. Drop the perpendicular from O to the sides AB, BC, and CA at M, N, and L respectively. Consider triangle OAM and triangle OAL. They are congruent by AAS. Thus, OM equals to OL. Similarly, consider triangle OBM and OBN. We have OM equals to ON. Combine the results. We have ON equals to OL. Now, consider triangle OCN and OCL. They are congruent by RHS. Thus, angle OCN equals to angle OCL. That is, OC is the angle bisector of angle C. In other words, the three angle bisectors intersect at O. As OM equals to ON equals to OL, the circle taking O as the center and OM the radius touches the three sides of the triangle. That is, the circle is inscribed inside the triangle, and O is the incentre. The logic of the argument for the concurrency of the orthotules is similar to the above two bisectors, but it involves more knowledge of circle. You may try and pause. Let the feet of orthotules from A and B be M and N respectively, and H is the intersection point of the two orthotules. Join CH and extend to the side AB at L. We would like to show CL is perpendicular to the side. First, we have AB, M, N are concyclic for converse of angles in the same segment. Also, we have C, M, H, N are concyclic for opposite angles supplementary. Then, from the first circle, we have angle ABN equals to angle NMA. The reason is angles in the same segment. For the second circle, we have angle NCH equals to angle NMH for the same reason. Combine the results, we have angle ABN equals to angle NCH or angle NCL. Therefore, B, C, N, and L are concyclic. The reason is converse of angles in the same segment. Thus, angle CLB equals to angle CNB equals 90 degrees. The reason is angles in the same segment. That is, CL is the orthotule from C, and the three orthotules intersect at H. The first part is done. The second part is about the intersection point. H is the orthocentre of the triangle ABC. Center is a feature related to a circle. We have already seen the circumcircle and incircle. So what kind of circle is H related to? Consider B, M, H, and L. They are concyclic due to opposite angle supplementary. Thus, angle LMH equals to angle LBH. As we have proved, angle LBH equals to angle NMH. We have angle LMH equals to angle NMH. That is, HM is the angle bisector of angle M. Similarly, we have HN and HL are the angle bisectors of angle N and angle L respectively. In other words, H is the incentre of the triangle MNL, the fifth of altitudes of the triangle ABC. So, orthocentre is really the centre of a circle. Now, the last type of special lines, medians. Their intersection point is called centroid, which is not a kind of center, but with a nice property that the point divides the median in the ratio 2:1. Let us check why the medians are concurrent and how the ratio is derived. The logic is still the same, but the techniques involved are not congruent triangles or properties of circle. We use another powerful technique, which is area of triangle. Let M and N be the midpoints of BC and AC respectively, and G is the intersection of the two medians AM and BN. Join CG and extend to meet AB at L. The area of triangle GBM and triangle GCM are equal, as the triangles have the same height and equal base. Let me denote the area by A. Similarly, the areas of triangle GAN and triangle GCN are equal and denoted by B. Denote the areas of triangle GAL and triangle GBL by X and Y respectively. Consider triangle ABG and triangle ACG. Since M is the midpoint, the triangles have the same base and the equal height, and thus we have X plus Y equals to 2B. Similarly, for triangle BAG and triangle BCG, since N is the midpoint, we have X plus Y equals to 2A. Thus, A equals B. Consider triangle CAG and triangle CBG. We have the same base and equal areas. Thus, their heights are equal, and therefore, AL equals to BL. That is, L is the midpoint of AB, or CL is the median. In other words, the three medians, AM, BN, and CL, are concurrent at G. To show the ratio, consider triangle ACG and triangle CMG. They share the same base and the ratio of the areas is 2:1, and thus the ratio of their height is also equal to 2:1. In other words, AG to GM equals to 2:1. This ratio applies to BG to GN and CG to GL similarly. This centroid is the center of gravity when the triangle is made by materials of uniform density. That means the triangle is unbalanced when it is supported at the centroid or the CG, the center of gravity. I have provided a proof of concurrency of each of the four special lines in a triangle. In fact, there are other methods to prove the concurrency, like by similar triangles, sine formula, and Sievert's theorem, etc. You may explore and enjoy it.